Hi.
Hi.
You have time, as you were. I'm just getting set.
Okay. I'm just downloading GeoGebra on this new thing because I think my computer might die before.
Oh,
Yeah.
okay. I don't want that to happen.
Yeah, no. College thing. This thing is bigger than my computer.
Yeah, it's crazy.
It's awesome. Polar R. Yeah. But dude, I didn't have to get a blue slip.
Oh, really?
Yeah.
Okay.
Because I told her that, I told her that I explained that Mr. Lancaster didn't put in one of my grades, so.
Yeah.
So when they did put it in, it was above.
Yeah. That's actually awesome.
I mean, this is the truth, so. It was awkward because I can't explain things very well.
Yeah.
So I was like, it's this thing does everything that a computer does.
I find it hard to type sometimes.
Do you have an iPad?
Mm-hmm.
Ryan, too.
Yeah.
I'm pretty sure this is the one that we're supposed to go.
Ja, Rang 1 und Rang 2.
Guess I'll just transition to this one. What else do we need to open?
I think that's about it.
Oh, Mr. Douglas?
Mm-hmm.
I was reviewing for the test with the definitions that you posted online or on the eCollege. And I think for rotation, with after you said that the angle, or angle P, I think you said angle PAP is equal to D degrees.
Did I make a mistake?
I think that angle PAP should actually be A prime.
Yeah. Okay, well, we're going to go to that sheet today anyway, so I'll fix it at that time.
Okay, great.
And I'll have lots more definitions, so I'll put up a new one.
Okay.
It's basically out of battery. Just push it away. Okay, I'm gonna use it.
I didn't know that Island would take so much out of it. Or out of mine.
Just gonna use it for GeoGebra stuff. Holy crap.
Okay. All right. Hey, Walter. What's happening?
Hi. There's something called CAV Games going on. It's like a school-wide competition events.
Oh,
Yeah.
okay. Even though the door is closed, now we can hear.
The door is closed.
Yeah, okay. All right. That's just, you're in noisy places. That's the second time. How was your science fair? Judging.
Oh, it was pretty good.
Good. You see some good projects?
They were okay. Some were pretty good, some were not so good.
Yeah, that's par for the course. All right, let's get started. Okay, the recording is started automatically. I've learned now how to share my screen properly. Are you guys, so Ryan, you have some new computer situation? What's your situation?
Yeah, our room, our GeoGebra, or our EMSON room that we have dedicated to just EMSON classes has some like tablets that act like computers, and they're actually pretty good. So I'm going to be using it instead. I downloaded GeoGebra and all. So
Okay.
I should be good.
Yeah, same here.
Oh, okay. Good. All right. Yeah, is your computer giving you a problem, Ryan?
Me?
Yeah.
It's just almost out of battery.
Oh, that's.
I forgot. This morning I was going through my backpack and I took out the cord for some reason.
I see. Okay. That sounded more serious. Okay. Not a problem. All right. Good. Yeah.
Logan and I took the test today, like an hour or so ago.
Good.
So,
Yeah.
Mr. Year should be sending that in.
Great. Super. Thank you. All right. And yeah. And you were supposed to do some revision on the, if you haven't done it yet, then do it soon. The revision on the symmetry definitions and proofs, although it may not be too necessary because we're going to do a lot with it today. All right, are you on, and no quiz today because the test, that's enough. And I'm also going to mention, I got some information about another possible topic that I'm going to look at, inversion in a circle, which is an interesting, my colleague Henry Picciotto recommended to me that that's something, it's an interesting, it's not an isometry, it's not a dilation, it's another transformation that is pretty interesting, evidently. I haven't looked at it yet, but I will, and I'll get back to you on that. All right. And you guys should get on Adobe Connect Friday, if you're not already. Ryan is already, and I made him and Logan is too. Okay, I made him a presenter. No. Make presenter there. Okay, now I got it right. So Walter is getting on. And, okay, so we're going to work through Adobe Connect. So now I realize, he said, Nelson set it up for me. If I share my screen, yes, then I can share the proper screen, which is this one. Okay, so I'm on the right screen. Good. So I'm going to share my screen on Adobe Connect. So it'll be in the recording. See, that was the problem, is it was recording just the Blue Jeans one, but now it looks like the right one. So I'm going to Adobe Connect. I'm going to share my screen. Adobe Connect comes up. And then I have to share my screen through Adobe Connect. And I want the main display. Okay, this one. And share this. Okay. So I am now going to get up Word. Okay, not this, but we haven't talked about this. Can you see fundamental theorem of dilations?
Yes.
Good. Okay. And Walter, you can see that?
Oh, sorry, what was that?
Can you see the fundamental theorem of dilation?
Yeah, I can see it. I can see it.
Okay. So I assigned you to read this, but we haven't talked about it. So my question is, it's really important, and I have to take some credit for this because I did this proof. And I had seen another proof that Professor Wu had done, which was much less. I have to say, it's not as nice as this. And then when I ran it by him, he didn't find a flaw, so that's good. So, do you want me to go? Do I need to go through it, or did you read it and you understand it, or somewhere in between? What's the story? Have you looked at it? I guess is my first question.
Yeah. Was this like 2 or 3 classes ago?
Yeah, it was, but we haven't talked about it, so I want to make sure that it's clear.
Okay. What are you at?
Actually, could we just go over just like a little bit?
Yeah, sure. Okay. So there are 2 parts of this. Walter's school is really thrilled with this theorem. So, all right. So it's really fundamental to the work on dilations and similarities. So the theorem says that if you have non-collinear if you have non-collinear points, and you think of C as the center of a dilation, and A and B are not on the same ray from that center of dilation, then the segment is going to be parallel, and it's going to have the same scale factor change that that the definition does, because if A prime and B prime are on the same line, if CAB are collinear, then the definition of a dilation is that A prime and B prime are also on the same line, and the distance gets multiplied by K. So, so this theorem extends that fact to points that are not on a ray from the center of dilation. Does that make sense, Logan?
Yeah.
Okay.
Yeah.
So the same thing happened, that it's parallel, its direction doesn't change, and that's crucial, right? I mean, in terms of the similarity proofs, that the direction doesn't change, and that gets multiplied by the same K. So, so the first part is that the direction doesn't change. The image of a line not through C is parallel. So this is the parallel part. And if you look at the diagram, basically, suppose it's not parallel, then the line through A and B, then the lines are going to meet. Yeah. If you take any line and dilate it, and the result is not parallel, then it's going to meet then the two lines are going to meet at some point. Call that point B. Okay? And then take some other point A on the line, and its image is A prime, because it's always collinear from C. So that's the situation, and that contradicts the definition of a dilation, because the scale factor from A to A prime is not 1, and the scale factor from B to B prime is 1. And that's impossible, because the scale factor has to be the same.
Okay.
Okay? So it has to be parallel. All right. And then, and now we have to show that it has, part 2 says we have to show that it has, the length of the image gets multiplied by K. So, again, look at this diagram. And here's C is the center of dilation, and here's A and B, a segment. And the parallel, we now know segment A prime, B prime. And I've labeled C, D, A, B on there, okay? And then on the next page, you see that K, which is the scale factor, is A plus B divided by A, by definition. That's the scale factor. And that also equals C plus D over C. All right?
Okay.
Now, now look at this next diagram. We draw a line through B parallel to A prime. That's this line here, BK. Okay? And now we dilate triangle ABC. So we do a different dilation. We dilate triangle ABC here from center B, but with a negative scale factor. And the negative scale factor is D over C. So that results in this figure. A goes into A prime here.
Okay.
Okay? And since dilation makes lines parallel, the image of AC is the image of this line here from A prime to C is from A double prime to B, and that's got to be parallel. So I've labeled that parallel. So these three lines are all parallel. Okay? And this line is parallel to this line. So Now, by the definition of a dilation, D over C is equal to F over E, because that's the scale factor of the new dilation, minus D over C. And if we add 1 to each of those fractions and simplify, make it into a single fraction, and just move it around, we have that C plus D over C. Now look at this. C plus D, which is this whole segment here, over C, right, is equal to E plus F over E. But that's exactly what we want, because C plus D over C is the scale factor, right?
Okay.
And E plus F over E is the ratio of A prime B prime to AB. So that ratio is the same as the scale factor.
Okay.
That's it. And an important corollary to this is that similar triangles have equal angles and proportional sides, because every isometry preserves side lengths and angle measures, and a dilation preserves angle measures because the image of any segment is parallel. That's why. So that's going to preserve the angle measure, is parallel to or collinear with its pre-image. So the direction, in other words, dilation preserves direction is another way to say that, a simple way to say it. So dilation preserves direction, and it preserves ratios of side lengths. We showed that for the third side of a triangle. We knew it was true for those. We knew it was true for segments that are collinear with the center of dilation, but now we've shown that it's true for segments that are not collinear with the center of dilation. It's true for any segment. Okay?
Okay.
So that's the proof. All right, done. Close that. Good. Now we are going to discuss this thing that turned out to be, I hadn't gone through it carefully, more difficult than I thought. And it's really interesting, actually, pretty challenging. So this is the 3 reflections, 6 cases. And we're gonna go through this, some of it slowly. So,
Okay.
So the first thing is we're going to look at the composition of 3 reflections. We did 2 reflections. So those are done. Now we're doing 3 reflections, and 3 reflections in 3 parallel lines. So I'm going to go to GeoGebra. And I'm going to get up Logan's file first. I don't have to do that. Did I get it up? Yeah, here it is. I don't want to save my changes. I just want to get the new file. All right. This parallel. All right. So now what I want to do is I want to get rid of the axes. This, yeah. Just want that. So what Logan did was he has a point G in the pre-image, and here are the reflection lines, and they're nicely labeled A, B, C. And we're going to reflect G first in A, and we get G prime. And then we're going to reflect G prime in the second line B, and we get G double prime. And we're going to reflect G double prime in line C, and we're going to get G triple prime. And now the question is, how can we go from G to G triple prime if we move G? This looks like a reflection, doesn't it?
Yeah.
Right?
Yeah.
Because as we move farther away, it gets farther away. We move closer, it gets closer. So it looks like a reflection. But the difficult question is, how do we find the line of reflection? And Walter started off the way I did, which was to try to mimic the argument that we had before with the distances being the same. You know, here we could have an x, x, y, y, and z, z if I move it a little closer. This, the distance from G to line A is equal to the distance from A to line to point G prime, and these two distances here are equal. The distances from G, between G and G prime to B are equal, and the distances between G double prime and G triple prime to C are equal. Yeah, okay. But that doesn't get us very far, unfortunately. So here's a hint. And this method or principle of proving difficult theorems has lots of applicability. And the principle is, take a simpler case. Start with that. And then once you get a simpler case, things can then sometimes be extended. Example, the Pythagorean theorem is a special case of the law of cosines. Did you realize that? You may not have been told that, but that's a special case. That's the first one you prove, and then you can expand it. You can expand it that way. And there are lots of examples like that. So, can you think of a special case? Can we put G in a convenient spot so that we could get a better idea of what's happening? Remember, we do know about reflections in two parallel lines. We do know that, and let's remind ourselves. A reflection in two parallel lines is equivalent to what?
A translation.
Right, a translation and more.
Isn't it? Double the distance between the parallel lines.
Double the distance between the parallel lines, and what about the direction?
It depends.
It's perpendicular to the parallel lines.
Yeah, perpendicular. And which does it go from line A to line B or line B to line A? Because there are two different directions there.
Yeah.
It's the same, except it has the opposite vector. Like it goes in a different direction, I think. Right?
Does it go from A to B? If we're reflecting first in A and then in B, does it go from A to B or B to A?
It goes from A to B.
Yeah, A to B. Right. Okay, Walter? Okay. So, can you think of a simpler case? Where can we put G?
You can put G on line A.
Okay, so let's put G on line A. And when we put G on line A, then G and G prime coincide. Good idea, Walter. All right, so now, how can we get now the other two reflections are reflection in these two parallel lines, right? And that's equivalent to what? We just said it.
Yeah. A translation.
A translation.
By from the double the distance of B to C.
B to C, that's right. Double the distance from B to C. Okay. So what we're going to do is a translation double the distance from B to C. Is that translation the same as a reflection? Is a translation double the distance? Well, it's not the same. But in terms of, obviously it's not the same. But in terms of moving the point, if we want to move the point G to G double prime, one way to do it is by a G prime to G triple prime, or G prime to G triple prime is what it should be. Yeah, to here. G triple prime is here. We want to move from G prime to G triple prime, and that translation is twice the distance from B to C. Can we accomplish that by a reflection? And if so, where's the reflection line? Yes, and where's the reflection line?
Wouldn't it be halfway in between?
Halfway in between, right. So it's a distance. What's the distance?
It would just be the distance BC.
Agree? Yeah, Logan, do you agree?
Yeah.
Walter, do you agree? Okay. So what we want is a line, the distance from B to C from this line A, right? Okay. So we need to get that distance. So suggestions on how to get that distance and make that.
You could connect G to triple prime, or G to G triple prime, and then use the midpoint tool.
Oh, good idea. Okay, so let's make a segment connecting G prime to G triple prime, and then let's use the. Where's that here? Yeah, midpoint. Oops. Okay, yeah, there's the midpoint tool. Now what do I select? 2 points or one segment. Okay. And now I want to make a perpendicular line. So that's here, perpendicular, okay? Line through this point. Okay. Now, I go to this move here, and let's move G. Okay. See how the line doesn't move?
Mm-hmm.
Yeah.
That's encouraging. And now let's reflect G in this line. So we go to this reflection tool, reflect about the line, and we pick the object and then the line. So we're going to pick G here and this line here. Bingo. Is that cool?
Yeah.
Just
all right,
added
so that worked.
So there's two here.
That worked. Have we proved it yet?
No.
No. So we found the line, but we haven't proved it yet. So that's what I want you to try for your homework. Is to try to prove it. Okay. That's a challenge. Similarly, so obviously the point, if the point is on line A, then we know it works. We did that. So a hint would be to pick a point not on line A and call the distance between that point and line A X. And then label the distance between A and B M, or that probably doesn't matter, and label the distance between B and C N. That's the important distance between B and C, and then play around with it and see if it still works if the point is off the line. All right, enough said. Okay, so we're going to close this and not save it. or should we save it? No. Okay. And then, oh, I should. Now I have to open GeoGebra again. Foolish person. I should have opened this.
A little.
I should have opened it without closing. I'm so used to closing first. And concurrent. And this I'm going to go a lot quicker on because there's a real analogy. You've noticed, I hope, the analogy between, I have to watch the time, between concurrent. So what I want to do, let's see if I get the graphics and I don't want this. Okay, so here we have a very similar situation where point E is reflected first in line A, then in line B, then in line C, and we found that for two lines, a reflection in two intersecting lines is equivalent to what?
A rotation.
A rotation
through double the angle that the pre-image makes with the line.
Yeah, from A to B, same thing. So this is very, very similar, right? So let's move line E and look at line E. Move point E and look at point E triple prime. What does this look like?
A reflection.
It looks like a reflection, doesn't it? Okay? And in order to, where should we start? What special case should we start with?
On line A.
Yeah. Okay? Enough said. So I want you guys to think about this. All right? And it's very similar. The result should be analogous to the previous in some way, right? And so instead of getting the rotation, can you mimic that result through a reflection? If so, where's the line? See, this time we're mimicking a rotation by a reflection. Last time we mimicked a translation by a reflection.
Okay.
Right? From that point, from that special point. And then we try to generalize. All right. Good. Okay. All right. Now, what I would, yeah. Okay, did that. Yes. Yeah, I want to explain your homework task. So, number 3, so your homework here is going to be, prove number 1, prove number 2, which is going to be very similar. And then we're going to split this up. This is tough. And all I want you to do is be prepared to explain your attempts. Okay? You may not get it. That's fine. I haven't tried it yet. But we'll see what happens. So I'm going to assign one of these to each of you. And it'll be on the, so this is 2 parallel lines and a transversal, basically. This is the reflection through 3 lines, 2 of which are parallel. And I'm going to assign 3A to Walter, and 3B to Ryan, and 3C to Logan.
Okay.
Okay? And that's going to be written. So don't try them all. Just try one, and we'll see what happens. It's an adventure. Okay. And we did that. Okay, now we're going to go to, close this. It is Valentine's Day tomorrow. That was my little reminder up there in the corner. And let's see. Right. The definitions. So uh, I'm going to go here to definitions. So I will update it. And you will notice that I did more on this. So I put in some basic definitions, and obviously there'd be more to add, but diagonal, and a diagonal, a kite could be what's called a chevron. So it can be concave, like this.
Okay.
Still has a line of symmetry. In that case, the bottom diagonal lies outside the figure.
Okay.
That's okay. So, I mean, some people say it's not okay. Let's just say it's okay. We want it to be inclusive. All right. And then a definition of a median of a triangle, an altitude of a triangle, angle bisector of a polygon. Those are useful. These definitions we've done already. Now what I want to do is make the symmetry definitions, and I'm going to rotate among you all. Write the symmetry definitions for special triangles and quadrilaterals, and we want these to be minimal, okay? So,
Yeah.
Isosceles triangle. Walter, let's start with you.
Well, there's one line of reflection, and it's through one of the vertexes.
One line of symmetry, we call it. One line of symmetry through a vertex. Right. Okay, let's go to Logan. Equilateral triangle. Well, yeah, Logan. Equilateral triangle. Let's try to make it minimal now. A minimal definition. Logan.
Threefold rotational symmetry.
Threefold rotational symmetry will work, but we can do better than that. So what about lines of symmetry? How many lines of symmetry do you need?
3. 3 lines of symmetry through each vertex, maybe.
Okay. Ryan, what do you say?
Oh, I guess you just need 2 lines of symmetry, so like a triangle.
We just need 2. So let's just say, sorry. Yeah, we can say a triangle. Let's just say 2 lines of symmetry.
Okay.
Through vertices. Now it turns out, Logan, that if you have 2 lines of symmetry, you have to have a third, and you have to have threefold rotational symmetry.
Okay.
So this is a good minimal definition. That's an interesting thing to try to prove, but not now.
Yeah.
Okay, Ryan, parallelogram.
A quadrilateral with two pairs of parallel lines.
We want a symmetry definition.
Yeah.
What's the symmetry of a parallelogram?
I'm not sure.
It's just
Okay, that's all right. Let's go to Walter. Walter, what's this? Oh, do you know?
Are we talking? Do we just want to do it with lines of symmetry, or can we also do it with?
No, rotational symmetry is fine.
Okay. With so quadrilateral with twofold rotational symmetry.
Twofold rotational symmetry. We have to locate the center.
Oh.
How do we locate the center?
Well, that would be the intersection of the 2 diagonals.
Right. Twofold rotational symmetry around the intersection of the diagonals. You're right, it's a quadrilateral. I'll put that in later. We know these are quadrilateral. Walter, kite.
There exists a line of symmetry through a pair of the vertices.
Let's say opposite. Isosceles trapezoid, Logan.
One line of symmetry. That's the perpendicular bisector of a side.
Minimal.
Through the midpoint of one side.
Through two opposite sides is enough. Has to be the midpoint. We can really do it minimally. As long as it doesn't go through the vertex, it's got to be. Do you realize why it has to be the midpoint?
You don't have to say it doesn't go through the midpoint?
You don't, because the line of symmetry makes the midpoints. Make it
that's clever.
It precipitates distance on both sides.
Got it. Okay, I've got it.
Good. Yeah, it's amazing. I mean, you can prove all this other stuff from that. We won't do it right now, but it's interesting. Rhombus, Ryan.
A rhombus is a diamond, right? Or can be called a diamond?
Yeah.
Okay.
Yeah.
So
Common name.
Two lines of symmetry through vertices.
Okay, Walter, rectangle.
Two lines of symmetry through opposite sides.
Now, I'll do the square. Square is two of these, right? Which two? Which two of these make a square that we've already done?
A rhombus and a rectangle?
Yeah. So it has four lines of symmetry.
A rectangle.
That's right. Four lines of symmetry. Two through opposite. Well, let's just say through opposite vertices and opposite sides. And the rotational symmetry follows from that. And then trapezoid, we're going to make an inclusive definition, which is not a symmetry definition. So we're going to say at least one. I'm putting in at least so we realize that a rectangle is a special trapezoid.
Okay.
Okay? All right. So we did the definitions. I'll post these. Now, theorems. Yes. Watching the time. Okay. So I did a lot more on the theorem list. So we'll go to the beginning. And we're going to fill in some more. Superimposing congruent segments by one or two reflections. So this is what we call theorem 1, 2, and 3. I don't like the numbers because then you start referring to them by the numbers, and that doesn't do it. So there were three important theorems. One is that the characterization of the perpendicular bisector as the locus of points equidistant from the endpoints. And this one is if you have two segments of equal length, you can map one onto the other by one or two reflections. And then we started this classifying isometries. And these were two very important theorems, that three non-collinear points and their images determine a unique isometry, really important. And an isometry is equivalent to the composition of at most three reflections. We've proved those. And now we want to analyze the cases, and we've started this. So one reflection is obviously a reflection. Two reflections we just talked about. Either the lines are parallel or they intersect. Three reflections we started to talk about. and we're going to finish this. Actually, now we can finish it because we talked about it. So successive reflections in parallel lines A, B, and C is equivalent to, the result of this theorem, it's equivalent to what?
Reflection.
Yeah, just
Reflection.
a single reflection.
Yeah, to a reflection.
What line was that?
I'm sorry.
What line?
It was.
Was that eight? Was that in
The midpoint between the first and the last.
Yeah.
Oh.
Did you hear that?
What about its
Oh, sorry. Yeah.
What about its direction? First.
Oh, it's in a perpendicular line. Or
How is it related to A, B, and C?
It's parallel.
Yeah. So it is equivalent to a reflection in a line parallel to A and B. And how can you describe its location? Walter, can you describe its location for me?
Well, like, I guess kind of generally,
Okay.
it's a distance. If you call x the distance between B and C,
Mm-hmm.
it's a distance x away from line A.
Okay, right. So, so let's see how to say this. Line parallel to A and B, and let's say the distance from B to C from line A. Does that make sense? Because we have to get the direction right, right?
Okay.
So the directed distance, I'm going to say, and the directed distance from B to C from line A. Is that awkward or is that good enough?
I think that's understandable.
Yeah.
It's
All right, I'll
it's
fix
good.
the italics and all that stuff. Okay, now successive reflections in A, B, and C that are concurrent at P, just by analogy. Can we get this by analogy?
Yes.
Okay, let's see what we do.
So it's equivalent to a reflection in a line concurrent to AB.
Yes. In a reflection in a line through P. Yes. And instead of talking about directed distances here, we're going to somehow talk about angles.
That'd be directed distance.
So the angle measure from B to C.
I think so.
for
Yes,
one.
I think so. Through
Yeah.
through P, through an angle. Through the angle from B to C. I think that's right. You'll find out. If we have to fix it, we'll fix it. But I think that's right. Because we no longer go from A. You know, it doesn't make sense. Okay. And then there'll be more. Because you guys will do number 3, and we'll talk about it, and we'll put those in there. And those are all leading up to the fundamental theorem. And the fundamental theorem will say, I mean, that every isometry, this is amazing, every isometry of the plane is either a translation, a rotation, a reflection, or a glide reflection. And Ryan, you were asking me why a glide reflection is important. This is the main reason why it's considered a basic isometry.
Okay.
Another reason is it provides symmetry to the not geometric symmetry, but a nice symmetry to isometries, because translation preserves orientation, rotation preserves orientation, right? Reflection does not, and glide reflection does not. There are two of each.
Put that on the tip.
And when you make the table, which we'll do in the future, I saw this. You can make a table of what happens when you compose one of these with another one of these. It's a 4x4 table. You know, what's a translation followed by a translation? What's a translation followed by a rotation? What's a translation? What's a reflection followed by a glide reflection, right? Those kinds of things. We could make a table for that, and that table has a very nice structure also. So there are all these nice reasons to include glide reflection, even though it seems like a composition. It's such a special composition. It's not just any translation followed by any reflection. It's very specific. And that extension really completes the isometries in a very nice way. So that's why. Okay. All right. Then I just put in some other theorems here. Watching the time. These are the basic angle and parallel theorems that we've done. That two lines are parallel if and only if the corresponding angles are equal. Vertical angles are equal. Alternate interior is a corollary to that. The sum of the angles of a triangle is 180. Exterior angles, the sum of the two remote interior angles. Then we had these congruence criteria that we proved. SSS, SAS, ASA. SAA is a easy corollary because the third angles have to be equal. HL we did. So there are 5 theorems like that. The fundamental theorem of dilation we just went through today. SSS similarity, you read. SAS similarity you did, and you did a good job on it. There's an AA similarity. Why don't we have ASA? Why is it AA instead of ASA?
Because the dilation, or wouldn't that mean that? I don't know how to say it.
It's because maybe if you have both of the angles, you have the third angle.
Yeah, but why don't we need the side?
Is it because AA is minimal?
Yeah. But why? Why does the side disappear? There's a nice correspondence between all these things, but there's no side here. Why don't we need a side? Because we're talking
if a triangle has two sides similar, or two sides that are congruent with with a similar triangle, then it's similar to any triangle with the same two angles within dilation.
Let me just say it. I mean, in order to have a proportion, you need 4 numbers, right? I mean, any 2 numbers have a ratio, and the value of the ratio doesn't matter. You only can talk about proportionality if you're talking about 2 sides. One side doesn't make any sense. I mean, any 2 sides have a ratio with each other.
Okay.
Right? So the side doesn't matter. We can always make a take a scale. So that's why you need at least two sides to talk about proportion, because you need four numbers. So that's why. All right. So now we go to isosceles triangle. So I wrote this. I wrote this down, and we're going to fill out some of these others. Okay. So properties. Isosceles triangle has lots of properties, right? Two sides congruent, angles opposite these sides have equal measure. And then I define altitude, median, and bisector of the angle to make it easy to say that they're all the same. They're all the same line of the angle between the two equal sides. They all coincide. For an equilateral triangles, everything coincides. That's nice. Let's start with kite, because we did all these properties of a kite last time. So I just want to list the properties in a similar way. Okay, so let's just go around. We'll go Walter, Logan, Ryan, and each one of you give me one property. So Walter, give me a property.
Of kites or parallelograms?
Kite. Let's start with kite, because we did that last time.
Okay. Well, I guess you have two pairs of congruent sides.
Logan, you're next.
One pair of congruent angles, or equal angle measures.
Yeah. Well, yeah. Either way, that's fine. Well, one pair of congruent angles, like you said, is fine. Ryan.
The line of symmetry bisects the vertices.
So this we'll say one diagonal bisects two opposite angles. Well, angles is bisects, right? Two opposite angles. Okay, Walter.
The diagonals are perpendicular.
Okay. Logan, there's one more about diagonals.
The line of symmetry is the bisector of the other diagonal.
Good. One diagonal bisects the other. Okay. Now let's go to, and notice, just notice quickly that the first thing we said, two pairs of congruent sides, that's the usual definition of a kite, right? But this time we're doing a symmetry definition, and this becomes a consequence that we proved. Okay, parallelogram. We're up to Ryan, I think, right? Give me a property.
Opposite side, or two pairs of parallel sides.
Yeah, opposite sides are parallel. Right. Opposite sides are parallel. Walter.
Opposite sides are congruent.
Good. Logan.
Opposite angles are congruent.
Ryan.
Do the diagonals bisect each other?
We do. Good. I think that's it. Okay, isosceles trapezoid. Walter.
There's a pair of sides that are parallel.
Good. Um, bases. Okay. Logan,
One pair of congruent sides.
right? Opposite. Let's say, let me think here. Non-bases, let's say. Non-bases, which are sometimes called legs, are congruent. They are. What can I tell you? Okay.
Consecutive angles, or
yes.
is it consecutive angles are equal?
Yeah. They're called base
They're
angles.
congruent.
Yeah, base
They're base
angles. Walter?
When the angles on like different bases are supplementary.
So angles on different bases. Consecutive angles on different. That's actually a pretty easy consequence of the parallel. So, can you tell me something about diagonals?
What are you looking for with the diagonals?
A relationship between them.
Oh, they're congruent.
Right.
Okay. It's like, what is?
Yeah.
Same thing.
Okay, rhombus. Logan.
Two pairs of congruent sides.
More than that.
And two pairs of congruent
sides.
angles.
No, sharpen that statement about the sides.
Oh, two pairs of congruent and parallel sides.
Yeah.
And
Wait. Ryan.
All sides are congruent.
Yeah.
oh yeah. It's a rhombus. I forgot.
Okay. All sides are congruent. Ryan.
Diagonals are perpendicular.
There.
Opposite angles are congruent.
Logan.
Lines of the diagonals are the lines of symmetry.
Yeah, but just properties now. What's another relationship between the diagonals? Yes, they're perpendicular. What else? It's 10 o'clock. All right.
Do they bisect each other also?
Yes, diagonals bisect each other. Okay. So, what I'm going to ask you to do, the last thing, say really quickly, is on the symmetry definitions and proofs, number 6 gives a proof of, so we can prove these properties pretty easily but how do we go backwards? Going backwards is not so easy. Given some of these things, can we prove that it has the symmetry? Okay? There's an example in number 6 that shows that if two opposite sides of a quadrilateral are parallel, then it has twofold rotational symmetry. So it's a parallelogram by our definition. I want you to pick one of those. That's what number 7 says. Pick one of these and show that some conditions imply the symmetry.
Okay.
Go the other way around. Okay? All right. That's done for today. Have a nice week.
I might not be here on Tuesday.
What's going on?
Since are you familiar with the Jets competition for high schoolers?
No.
Oh, okay. So it's like a engineering competition, I guess.
Uh-huh.
And so I'll try to get on during a break, but I don't know if I'll be able to.
Okay.
And then on Friday, I won't be here because I'm going to the Harvard math tournament.
Holy cow. Okay. All right. I'll have Ms. Sobe send you the recordings.
All right, thank you.
Okay. All right. Have a nice weekend, you guys.
I'm not going to be here on Tuesday also.
Only
It's just going to be
one.
Ryan. Yeah.
What's going on?
I've got a college visit,
A college.
or like an overnight college
Okay.
visit, so yeah.
All right. Thanks for telling me. I'll mark those. There are a limited number of absences. I think it's 5.
5, okay.
For the course. So be aware of that.
Got
Okay. All right. Good.
Well, I'll see if I can get on during, but I don't know if I'll be able to make it.
Yeah. Okay. If you can, you can. You can't, you can't. Ryan,
I'll
you'll
be here.
here. Okay. All right. We'll see you. Have a nice weekend, guys.
Yeah.
Bye.
Bye.
Wait.